Hello everybody. Thank you all for watching my channel. I hope you all can have a good time and clues with this video. I made this video using the GEPHI software and also the Bridging Centrality BriCe plugin. We developed the BriCe plugin for GEPHI as part of a master's thesis of a student guided by myself in 2018. In advance, I can say you all will need Java installed on the computer to reproduce it. Java is the main prerequisite for GEPHI. The BriCe plugin is available from the additional GEPHI libraries. I will try to give you a glimpse of centrality measures. Centrality measures are mighty because we can get a lot of information of relationship data among several kinds of objects. For example, our contacts on the internet and social media, but my main focus here is to show you how centrality measures can search for new vaccine candidates. Well, for doing that, I will show you a small sample. This presentation should not take much longer because this is a straightforward example, and will be enough for all of you to have a clear view of what I'm talking about. Let me show you. I have many files in this folder, but I will start with this file. This is a dot file. This is one of the most straightforward ways to construct a graph. Here I have a lot of objects. I don't care what about means A, B, C, D. It could be a person, it could be a computer, anything you want. They are entities that are related. The way that they are related is defined by these two minus signals. It means a relationship between entity A and entity B, A and C, and so on. Looking at these relations separately, we can't have any clues about what kind of natural structure. Still, when you start a program like GEPHI, opening this file, things begin to change. The first thing that GEPHI told us is that we have 11 nodes, or vertices, and 12 edges. I will start this small toy of a graph in a new workspace. Let's say that those relationships I showed you a few seconds had weights. If it was the case, we could command the GEPHI tool to sum those weights in case we find two or more relationships between A and B, for instance. This small toy that I will open here does not have weights associated with the edges, so such a configuration is not essential. Let's open the new workspace. Now we have a lot of dots connected by edges. Looking to this web is very difficult to find out some structural information. We need to apply a layout for this graph in GEPHI. We have many layout options. For example, I like a lot of this infon HU layout. Let's see what happens. Wow, very more interesting. Don't you think? Now you have a central dot connecting two tiny clusters of dots. We can find a lot of structural information with this graph, looking for the statistics. Let's see this menu, for example. We can find out the average degree. Let's see that. Here we have 6 nodes with a degree of 2, 2 nodes with a degree of 1, and so on. Okay. We now can discriminate these nodes using a slight trick of GEPHI that is coloring each node according to a partition. Let's see that. Let's choose an attribute. The only attribute we have until now is the degree. We can apply, for example, this partition according to the number of edges entering or leaving each node. For example, now we have the nodes colored by the number of edges. Another possibility is to rank all the nodes according to a degree. Let's use this scale from white to dark green. We can color all the nodes according to the most significant number of degrees. The largest number of edges are found in these vertices. Because of that, we have a darker green related to these vertices. The other nodes with smaller nodes than this one have a slightly more transparent green color. Okay. Let's see how the data laboratory. The data laboratory gives us information about the data associated with our graph. For example, I have node A with degree 4, B with degree 2, etc. Here we can have a lot of data associated with each vertex, or even in each edge. The only information associated with the degree is in this graph, because I asked GEPHI to calculate the degree. After that, we have the degree incorporated into the data laboratory. Now, I will ask GEPHI to calculate another centrality measure called Bridging Centrality. Let's see that. The number of calculations made by this algorithm can be tremendous according to the number of edges and nodes in our graphs. However, as I told you before, this is an elementary graph. So the computation time was speedy. Now, in the data laboratory, we have more data associated with each node. We have the betweenness centrality, and now we can sort the data according to each attribute. The bridging centrality is the main focus of our analysis right now. But before I talk to you about bridging centrality, I should introduce you to other necessary measures to calculate it. I already show you the degrees centrality. Now, I will talk to you about the bridging coefficient. The bridging coefficient is the opposite of the degree centrality. Let me show you. For example, we have this visual output if I apply a ranking calculation to this graph based on the bridging coefficient. You can note that the nodes possessing a smaller number of edges are the most colorful ones. That's because we have bridging quantities like the inverse of the degree. I will show you once more the degree ranking. Can you see now that the nodes possessing the more significant number of edges are the most colored? The betweenness centrality is a more complicated measure to explain, because it considers all possible paths connecting the nodes of this graph literally. We are talking about all possibilities to connect any pair of nodes depending on the size of the graph. This number of possibilities to traverse the graph, connecting any arbitrary pair of nodes, can be enormous. The betweenness centrality will consider the number of paths traversing a specific node, divided by all possibilities of crossing the network connecting a pair of vertices. So, it's a kind of normalization. It gives us a perspective of how important a node is for this graph according to the number of possible ways to traverse the graph, connecting any pair of points. You can see here in the graph that this node is crucial concerning the possibilities to traverse the graph connecting any kind of vertices. This is the reason why this dot is the most darker green in the graph. This is the most critical dot in the graph connecting all possible pairs of nodes. Said that, let me talk about the bridging centrality. The bridging centrality is a measure resulted from the multiplication of the betweenness centrality and bridging coefficient. We have the greenest dark dot here, meaning that this node acts like a bridge connecting clusters of nodes. That's precisely the case of this central dot here. Here we have two tiny clusters of dots, and this central dot has the role of connecting both groups. So we can clearly see that this is the product of betweenness centrality and bridging coefficient, because we have an inverse degree multiplied by the betweenness centrality. This dot has both characteristics. It's essential to traverse the graph. It is vital to traverse the graph connecting any pair of dots, and at the same time, it has one of the most minor numbers of edges. Not necessarily the smallest one, and also is very important according to betweenness centrality. We saw before that this node here is the most crucial form of betweenness centrality. This one has a significant value for betweenness centrality. Despite this, it is not the most effective. I told you that my main focus is a biological point of view talking about interaction networks of proteins. If we consider a network like that, one can think about this dot like a protein. This protein can have a significant biological role to connect, for example, two molecular processes. Let's assume that these two clusters represent proteins associated with two different molecular processes. Let's suppose that a bacteria needs one protein to connect these two clusters, these two processes. Supposing that such a kind of dependence exists for these two clusters, one can imagine the possibility to block this process by neutralizing this protein. Suppose you think about this process like a disease, for example. In that case, one can believe that if I neutralize this gene, this protein, I can cancel the infection of the bacteria. So, neutralizing the bacterial disease, we can use this bacteria, for example, to construct a vaccine. A vaccine of bacteria could alarm our immunological system, but not be capable of causing the disease. We had neutralized the two more critical molecular processes for disease characterization. This is an elementary example. We all know that a genome has several thousand genes. So, we cannot expect to find just a single gene as the main connector of just two processes that can neutralize a disease. But let's suppose you can have the success to identify several genes with vital bridging roles. We can have a chance against the bacteria. This is not a simple task. It demands a lot of research, and not only bioinformatics research. Everything you predict here in the computer is just the beginning to be proven in the wet lab. I used to call this the dry lab, and the dry lab is today the start point for the wet lab. Here, the computer, we are looking for clues about what proteins we need to study in a set of several thousand genes. Clues like those can be very precious. It can save us a lot of time and money. For now, it's all people. Thank you for your attention. Bye.